Yeah. Next one is determinant x cube 1 y cube 1 z. This is equals to x minus y z z minus x into x plus y plus z. Am I clear? Now third one is determinant 1 sorry. Third one is 1 x square x cube 1 y square y cube 1 square z cube. That is equals to x minus y minus z, z minus x, xy plus yz plus zx plus zx. And the last one, which is the most important, is xyz, yzx, and zxy. It is minus of x cube plus y cube plus z cube minus 3xyz. Now, if you remember, its factors are minus of x plus y plus z into x square plus y square plus z square minus xy minus yz minus zx. Am I clear? And that is also can be written as x plus y plus z into x minus y whole square plus y minus z whole square plus z minus x whole square whole divided by 2. Fair enough? So these are the 4 determinants that frequently we see questions from these topics. Now see, there's a question: if x, y, z are the sides of a triangle and they follow this property, that means what kind of triangle it is? Tell me, Madhukar. If x, y, z are the sides of a triangle and they follow this, like this is 0, then what kind of triangle it is? The kind of triangle it is like x minus y should be 0, or y minus z should be 0, or z minus x should be 0. That means it is an isosceles triangle. But now if they say that x, y, z are the sides of a triangle and this is 0, this last determinant, it is 0. If x, y, z are the sides of a triangle and this determinant is 0, that means it has to be 0. So this right side equal to 0 only exists when x equals to y equals to z. Otherwise, it won't happen. Am I correct? So remember these ones. All right. Now, properties of determinant में we'll just go through small properties. If any two rows in any determinant are identical or any two columns are identical, the value of the determinant goes 0. है ना? So if any two rows are proportional or say they are identical, the value of the determinant being 0. Next is if all the elements of a determinant goes 0, or I should say all the elements of any row of a determinant goes 0, the value of determinant is 0. Now, if A transpose is transpose of a matrix, then determinant of A is determinant of A transpose. Am I clear? Now, if we interchange any two rows in a determinant, its value changes in sign only. So if you reshuffle any two rows, then its value will change in the sign only. Positive will get negative, negative will get positive. Now, if the elements of any row of a determinant be multiplied by a constant k, the value of the determinant gets multiplied by that same constant. Fair enough? So very small properties you are already aware of. Okay. If I ask you a question, if determinant 1 x square 1 y square 1 z is plus determinant x square x cube y square y cube and z square z cube, this is 0. Find the value of x, y, z if x is not equals to y, which in turn is not equals to z. Yes. Take a moment. Give me the correct answer. Yes, yes. Quickly, quickly. What is the value of x, y, z? See, take x common from this row, take y common from this row, and take z common from this row. All right. So what do you get? Determinant 1x x square, 1y y square, 1z z square plus xyz into 1x x square, 1y y square, 1z z square. This goes 0. So if I take this 1x x square, 1y y square, 1z z square common, so I get x minus y minus z minus x into 1 plus xyz equals to 0. Now, in the question, they have already mentioned this is non-zero. That means xyz is equals to minus 1. All right. Now, very, very important property with respect to solving determinant in an easier way. In any row, say R1, in any row, we can always add same multiples of any other row. Means R1 ko we can write R1 as R1 plus 2R2 minus say 3R3. So you can add or subtract same multiples of any other row or any other column. So value of the determinants remain unchanged with this. Am I clear? So in any determinant, uh, you can add same multiples of any other row or any other column and the value of the determinant remains unchanged. Like here in R1, I added twice of R2 and subtracted thrice of R3 and the value of the determinant remains unchanged. Am I clear? So this is very important while solving those determinants which are complex in calculation. So we simply add or subtract, and the prime agenda behind this calculation is make the elements of any one of the rows or any one of the columns as 1. So once you make all the elements of any row or any column 1, you apply the subtraction property and you will get two elements as 0. Got it? Now, expansion of the determinant. If in the elements of any row or any column, the respective cofactors are added, the respective cofactors are multiplied and the quantities are added, the value of the determinant you obtain. Got it? So value of the determinant can be obtained if elements of any row be multiplied by their respective cofactors and added. Fine. Also be very sure if in the elements of any row you multiply the cofactors of any other row and then you add, you get 0. See the last point. But if the elements of a row are multiplied with the cofactors of any other row, then the sum is 0. Sum is now area of a triangle using determinants. If x1, y1, x2, y2, x3, y3 are the vertices of a triangle, then area of triangle will be half of x1, y1, 1, x2, y2, 1, x3, y3, 1. Audit expansion you don't have to remember. And now if these points are collinear, that means the triangle is non-existing. That means this is happening. x1, y1, 1, x2, y2, 1, x3, y3, 1 goes 0. That means points are collinear. Am I clear? Now let's come to matrices. Then we will do some questions over it. So important property about matrices is matrix addition is commutative, means A plus B is B plus A. You know that. And see, I will also repeat, if we add two matrix, what do? We add the corresponding entries. Like a 2 by 3 matrix can be added to another 2 by 3 matrix only. Two matrix can be added if their order is same and the resultant is the addition of corresponding entries. Fine. Now, if matrix addition is also associative, means A plus B may you add C or A you add to B plus C. One and the same thing. Now, alpha times A plus B is alpha matrix A plus B, alpha matrix B, where alpha is any scalar. Alpha plus beta into A is alpha A plus beta A. Now, alpha beta into matrix A is alpha beta into matrix A, where alpha and beta are two different scalars, two same scalars. Now, most important, matrix product is not commutative. AB is not equal to BA. And that is the only reason whenever we have to write A plus B whole square, we directly don't write it A square plus B square plus 2AB. This is not correct. So what do? It is A square plus B square plus AB plus BA. So matrix product is not commutative. So whenever this happens, like A plus B whole square is A square plus B square plus 2AB, that means we say AB equal to BA. That means we call it matrices A and B, they commute each other. Matrices A and B, they commute each other. Got it? Okay. Identity matrix commute with every matrix. So IA equals to A equals to AI. Now, matrix product is associative. A plus B may you multiply C or you multiply A to B plus C. That is also one and the same thing. Now, matrix product is distributive, means A times B plus C is AB plus AC. Fine. Now, transpose of a matrix. So let A and B be two M is to N matrix, and a matrix is obtained by interchanging the rows and columns of matrix A. Then we are aware that it is called transpose of matrix A. That means if A is A, B, C, P, Q, R, then A transpose is A, B, C, P, Q, R. Am I correct? A is A, B, C, P, Q, R. Then A transpose is A, B, C, P, Q, R. But you see, first row became first column and second row became second column. So if it is a 2 by 3 matrix, it became a 3 by 2 matrix. Got it? Now, properties of transpose of a matrix. If A and B are two matrices of order M by N, then A plus minus B transpose is A transpose plus B transpose. Distribute transpose to individual matrix. If K is a scalar, then K A transpose is K times A transpose. Fine. Third is transpose ka transpose is again original matrix. Fourth is very important. This is what we call the reversal law of transpose. That is AB transpose is B transpose A transpose. That can be extended to more number of matrices like ABC transpose is C transpose B transpose A transpose. Fine. Now, A to the power N transpose is A transpose to the power N. This is direct repercussion to fourth property. This one. Got it? Now, see, there are some special matrices. I'll talk about all of them later on. First of all, two very special matrices. One is symmetric matrix. Symmetric matrix. Other is skew symmetric matrix. So as you all are aware already, symmetric matrix, it happens when A transpose is equals to A. Symmetric matrix is when A transpose is equals to A. And skew symmetric matrix when A transpose is equals to minus A. That means A plus A transpose is getting 0. Got it? What happens in skew symmetric matrix? That its diagonal entries are definitely 0, and it is off diagonal entries may be 0, may not be 0, and conjugate entries, they are negative of each other. Like if it is P, it is minus P. If it is Q, it is minus Q. If it is R, it is minus R. This is a skew symmetric matrix of order 3. Skew symmetric matrix of order 3. So what is happening? Diagonal entries are 0. Off diagonal entries, they may be 0, they may not be 0, but conjugate entries, their sum is 0. That means Aij plus Aji is getting 0. Understood? Now, what is happening in symmetric matrix? Conjugate entries are identical. That means if it is, they are, say this is ABC. If it is P, it is also P. If it is Q, it is also Q. If it is R, this is also R. Got it? So this is what we call symmetric matrix. So this is A. Now, very special thing is A transpose is A, and here A transpose is minus A. Fair enough? Have a look. Matrix, value of odd order skew symmetric matrix, value of odd order skew symmetric matrix is always 0. Determinant of A is always 0 if A is a odd order skew symmetric matrix. Determinant of A is 0 if A is a odd order skew symmetric matrix. Now see some special matrices. Uh, they are very rarely asked in JEE and they are tough to remember. But I still insist you whenever you go for any paper, just recall these things right before the exam. So a matrix is called idempotent matrix if A square is equals to A. A matrix is called idempotent matrix if A square is equals to A. Now, a matrix is called nilpotent matrix. Another definition is nilpotent matrix. So, a matrix is called nilpotent matrix of matrix if it satisfies the relation that our K is a null matrix. And in that case, the least value of K is called the index of the nilpotent matrix. The least value of K is called the index of the nilpotent matrix. Now, a square matrix A is called involutory matrix. A square matrix A is called involutory matrix if A square is equals to I. A square matrix is called involutory matrix if it satisfies the relation that A square equals to I. Now, a square matrix A is called orthogonal matrix if it satisfies the relation A transpose is I. A transpose is I is also equals to A transpose into A. So a square matrix A is called orthogonal matrix if A transpose is I. Symmetric matrix, I have already told you. Square matrix is called symmetric matrix if A transpose is A. This is called skew symmetric matrix if A transpose is minus. Got it? Now, base of a matrix is nothing different. It is just the summation of the diagonal entries of a square matrix. Got it? So, if a square matrix A is A, B, C, P, Q, R, X, Y. Trace of A is of the diagonal entries trace matrix. Now, write a small question. How many matrices? How many matrices of order 3 can be formed using 1 minus 1 and 0, using 1 minus 1 and 0 as its entries, and and trace of A is 0. Yes, tell me. How many matrices of order 3 can be formed using 1 minus 1 0 and its as its entries, and trace of the matrix A is 0? Yes, tell me. Now see, trace of A 0 means A plus Q plus Z is 0. Now, how is it possible? If I take diagonal as 1 minus 1 0, that is okay. Trace will go 0. Or if I take diagonal as all 0, trace will be 0 if entries are 1 minus 1 0 or all entries 0. Now, in this case, you can form the diagonal in 6 ways. In this way, we can form the diagonal in 6 ways. And in this way, this is the one way to form the diagonal. So, number of matrices will be what? Number of matrices will be 7 into. Now, each entry, or out of the remaining 6 entries, each entry can be filled in 3 ways. 1 minus 1 0. So, it is 3 to the power 6. That is 7 into 3 to the power 6. Am I clear? 7 into 3 raised to the power 6. Now, invertible matrix. A square matrix A of order n is said to be invertible if there exists another matrix B. See, if product of two matrices goes identical, if product of two matrices which are compatible for the product, if their product is identity matrix and they are commuting each other, means AB equals to BA, it is an identity matrix. That means A and B, they are inverse of each other. Am I clear? If product of two matrices is an identity matrix, they are compatible for the product, and AB is equals to BA is identity matrix, that means A and B are called inverse of each other. Now, basic properties about the inverse is, inverse of a matrix is unique if it exists. If inverse of a matrix exists, it is unique. A into A inverse is A inverse into A is I. A and B are invertible, then A inverse. This is what we call reversal law of inverse. Now, A inverse will also symmetric, and every orthogonal matrix is invertible. Every orthogonal matrix is invertible, and its inverse is its transpose. Got it? Every invertible, and its inverse is its transpose. Fine. Now, adjoint. This is again very important thing, adjoint of a matrix. Say a square matrix is given to you as Aij. It is of order 3 by 3. It can be of 2 by 2, can be of any order. Now from this matrix, form a matrix whose entries are the corresponding cofactors of the entries of matrix A. Now make a matrix C. C is what? Cij, it is also 3 by 3. Where what is happening? Cij is cofactor with respect to Aij. Now take transpose of C. And this is what we call, and this is what we call adjoint of A. All right. Again, I repeat, a given matrix to you is A. Make another matrix whose entries are the cofactors. Entries are the cofactors of matrix A. Then take the transpose of C, which is your adjoint of A. Then take the transpose of C, which is your adjoint of A. Now, if this is your A, then adjoint A is what? It is the transpose of the matrix formed by the cofactors. All right. See, in case of 2 by 2, you can directly remember adjoint is what? Change the diagonal entries and change the sign of off diagonal entries. See, AD became DA and change the sign. B became minus B and C became minus C. So in case of a 2 by 2 matrix, in case a 2 by 2 matrix, adjoint of A is change diagonal entries and change the sign of off diagonal entries. Am I correct? Now, properties of adjoint of matrix. Adjoint of A into A is A into adjoint A, that is determinant of A into In. Adjoint A into A is A into adjoint A is determinant of A into In. Got it? So see, from there only you can judge if A into adjoint of A is determinant of A into In. So can I write A into adjoint of A upon determinant of A as In? That means product of these two matrices is an identity matrix. That means they are inverse of each other. So A inverse of upon A. And from this point, we can very clearly say that A inverse will be existing. Unit of A goes non-zero. Got it? There comes a definition, singular matrix. Singular matrix. A matrix is non-singular. Fair enough. Its determinant should not be zero. Now, A to the power n property, determinant of adjoint A is determinant and adjoint of adjoint A determinant is determinant of A raised to the power n minus 1 square. Adjoint of adjoint A So adjoint of determinant of a raised to the power n minus 1 whole square. Fine. Now again same thing, inverse of a matrix is adjoint A upon determinant of A. So if A is a non-singular matrix, square matrix, then inverse of X is this. Got it? Now, this is the most important topic from this section. If 100 questions are asked from this, 80 questions are from this only. Solution of the system of linear equations in 2 and 3 variables. We'll talk about the 3 variables only. 2 variables are already covered in this section. Now see, you have 3 questions. A1x plus b1y plus c1z is d1. A2x plus b2y plus c2z is d2. And A3x plus b3y plus c3z is d3. Got it? Now the solutions of this system is, what do I have? X is dx upon d, y is dy upon d, and z is dz upon d. Got it? Now d is what? D is the determinant formed with the coefficients of x, y, z. That is a1, b1, c1, a2, b2, c2, a3, b3, c3. Now dx is what? Now delete the column containing coefficients of x, that is a1, a2, a3, and replace d1, d2, d3. So d1, d2, d3, b1, b2, b3, and c1, c2, c3. What is dy? That is a1, a2, a3, d1, d2, d3, and c1, c2, c3. And what is dz? dz is a1, a2, a3, b1, b2, b3, and d1, d2, d3. Now, this is what I have, d1, d2, d3. Got it? So, about this system of equations, Now, this system is either consistent or it is inconsistent. So system is either consistent or inconsistent. Now consistent is what we call at least one solution. At least one solution. And inconsistent is what we call no solution. Fine. Now consistent further contains 2 categories: unique solution or infinite solution. Consistent may we have further 2 categories: unique solution, infinite solution. Now, since we are already aware of 3D geometry, you can see these are the equation of 3 planes. Now, 3 planes will either have a unique solution, they will intersect at one point, or these 3 planes will be having directly infinite solution if they have a common line of intersection. Am I clear? So these are the 3 planes. These 3 planes, either they will be having a unique solution, that is single point of intersection, or they will directly be having infinite solution. There is no case like these 2 planes are intersecting at 2 points, 2 planes are intersecting at 3 points. So they will be having a unique solution or directly infinite solutions. So for unique solution, D should not be 0. D is what? That is the determinant made by the coefficients of x, y, z. This D, this should not be 0. Am I clear? So for unique solution, this D should not be 0. Now for infinite solution, this D should be 0 as well as D1 D2 and D3, they all should be 0. So for infinite solutions, D should be 0 as well as D1, D2 and D3 should be 0. And inconsistent solution is directly no solution. That means D should be 0, but at least one of D1, D2 or D3 should not be 0. So for inconsistent solution means no solution, D should be 0, but at least one of D1, D2, D3 should not be 0. There is a very special case also. Like we have a system of equations like this: A1x plus B1y plus C1z equals to 0. A2x plus B2y plus C2z equals to 0. And A3x plus B3y plus C3z equals to 0. Like we have this system of equations. Now you see 0, 0, 0 is already a solution of this system. Okay? That is what we call trivial solution. So when 0, 0, 0 is a solution, we call it trivial solution. Got it? So it's a trivial solution. Now they are saying the system is having non-trivial solution. That means it is having non-zero solutions also. So if system is having non-zero solutions also and 0, 0, 0 is a well-known solution, that means system is directly having infinite number of solutions. And if system is having infinite number of solutions, its D should be 0. That means determinant of A1, B1, C1, A2, B2, C2, A3, B3, C3. This should be 0. Am I clear? Now, see, there is a question in previous year JEE means this year only. If the system of equations has infinitely many solutions, then find the value of 13 alpha beta. Go for it. If the system of equations is having infinitely many solutions, then find the value of alpha, beta, gamma. Yes, please do it. Mark your answer in this poll. What are the conditions for infinite solution? D should be 0 as well as D1, D2, D3 is 0. Yes, yes, please, please. Now see, this is the hard work behind this question. You have to calculate D as well as D1 as well as D2 as well as D3. Make all of them 0. You will get alpha as minus 70 and you will get beta as minus 16 upon 13. So alpha into beta will be 16, 112 upon 13. So 13 alpha beta is equals to 1120. This much of hard work is required here. D you make 0, D1 you make 0, D2 0, D3 0. You make all of them 0, only then you get the correct answer. Fine. Okay, now do this question. Let A is 201, 110, 101 and B is a matrix B1, B2, B3 having columns as B1, B2, B3. Got it? Now A1 is 100, not A1, this is AB1. AB1 is 100, AB2 is 230, AB3 is 321. Fine. Now, if alpha is determinant of B, if alpha is determinant of B and beta is the sum of all diagonal elements of B, that is trace of B, then find alpha cube plus beta cube. Yes, please. Now see, let us assume this B1 is a column matrix x1, y1, z1. Now AB1, that means 201, 110, 101 multiplied by x1, y1, z1 is 100. If you multiply this, you get 2x1 plus z1 is 1, x1 plus y1 is 0, and x1 plus z1 is also 0. All right. If I simplify all of them, I get x1 as 1, y1 as -1, and z1 as -1. Take a look. So, similarly, if you apply AB2 as given to me as 230. So from this, you will get B2 as 20 minus 1. And similarly, if you do AB3 as 321, in that case, B3 you will get as 20 minus 1. Uh, 21 minus 2. Here we will get 21 minus 2. 21 minus 2. So with this, you got B1, B2, B3. So you got matrix B. Now the matrix B is 1. B1 is 1 minus 1 minus 1. Then 2, 1 minus 2. Then 20 minus 1. Understood? Now trace of B, that is sum of the diagonal entries of B is 1. And determinant of B will come 3. This is your alpha and this is your beta. Now they are asking for alpha cube plus beta cube, and that will be 28. Yes. Now, this was easy. Go with this question. Alpha for which value of alpha for which this determinant is 0 lies in the interval. Now see, the only agenda is you simplify this determinant. Only agenda is will be your answer. Yes, please. Now let's do it. So if I simplify it, I get 2 alpha plus 3 into 7 alpha upon 6 minus 3 alpha plus 1 into minus of 7 by 6 is equals to 0. If you simplify it, you get a quadratic in alpha. So it is 2 alpha square plus 3 alpha plus 3 alpha plus 1 equals to 0. So it is 2 alpha square plus 6 alpha plus 1 equals to 0. So alpha is what? Minus 3 plus under root of 7 upon 2 and minus 3 minus under root of 7 upon 2. So the values of alpha, they are in interval B. All right. So now you need to practice more from this section. Take any book having PYQs from JEE mains and practice it. Practice as many as you can. This is a scoring chapter having not so many variations. Fine. That would be all from my side today.